So, in this lecture we will talk about some of the energy theorems and weak form of the governing differential equation. In the last class we dealt on the theoretical basis for FEM and we briefly introduced the weak form on a general differential equation. So, today we will talk about the theorems that led to the weak form and also the energy theorems based on which the weak form will be constructed for some structures we normally use in microsystems such as beam structures. So, before we go into the energy theorems, we need to understand basically the theory of elasticity. In theory of elasticity, there are 15 unknowns, which are the 6 stress components, the 6 strain components and the 3 displacement components. So, if you have a coordinate system which is given by say x, y and z direction and the stress is a tensor having both the direction and the plane of applications, the 6 stress components are sigma xx, sigma yy, sigma z, tau xy, these are shear stresses, tau yz and tau zx. And we have 6 strain components corresponding to stresses which are epsilon xx, epsilon yy, epsilon z. We have gamma xy which are shear strains, gamma yz and gamma zx. And we have 3 displacement components in the 3 coordinate direction, which is u, v and w. So, in all we have 15 equations, 15 unknowns and we need 15 equations to solve. Let us see where we get these 15 equations for. Out of which we have 3 equations of equilibrium which are given by d sigma xx by dx plus d tau xy by dy plus d tau xz by dz, which will be equal to rho into u double dot. U double dot is which is equal to rho into d square u by dt square. Similarly, this is the equilibrium in x direction. So, similarly we have d tau xy by dx plus d sigma yy by dy plus d tau yz by dz, which will be equal to rho into v double dot. This is the y direction and we have dou tau xz by dx plus dou tau yz by dy plus dou sigma z by dz, which is equal to rho into double dot. This is the z direction equilibrium. So, these are the fundamental equations of equilibrium which he has to solve. Next set of equations are the 6 stress strain equation, which is given by what is called the Hooke's law, which basically relates the stresses and strains with a matrix sigma will be equal to, which will be a vector, sigma will be equal to some C matrix into epsilon, where we have the 6 stress components sigma xx, sigma yy, sigma z, we have tau xz, tau xy, tau yz, tau zx. So, these are the stress vectors which is related to the strain vector, the constitutive matrix. This is called C11, C12 to C16, C21, C22, C26 and then you have C61, C62, C66, which is related to the strain which is given by epsilon xx, epsilon yy, epsilon z, gamma xy, gamma yz and gamma xz. So, there are 6 equations here and the C11, this is a 6 by 6 matrix, and in this matrix we always have C12 equal to C21. So, it is symmetric. So, there are only 21 independent constants. By taking planes of symmetry, different planes of symmetry, we can reduce it to only 2 constants in the case of isotropic structures, which are basically the Young's modulus and Poisson's ratio. Nu is the Poisson's ratio. If it is an orthotropic structure, we have 9 constants, and if it is a transversely isotropic, we have 13 constants. Like that, we can actually reduce depending upon the plane of symmetry. But in this lecture, we will be talking only about isotropic structure. So, basically we will be dealing with only 2 constants, that is the Young's modulus E and the Poisson's ratio nu. Then we have this 6 strain displacement component. For example, we have epsilon xx, which is the strain, is related to displacement du by dx. Epsilon yy will be equal to dv by dy. Epsilon z will be equal to dw by dz. Then we have the gamma xy, which is equal to du by dy plus dv by dx. Then we have gamma yz, which will be dw by dy plus dv by dz. Then we have gamma xz, which is equal to dw by dx plus du by dz. So, we have 6 strain displacement relationships. So, in all we have about 15 equations for determining the 15 unknowns. So, in addition to having these 15 equations, the equations has to satisfy the boundary conditions. In the last class, we talked about essential boundary condition, which is on the primary dependent variable. If we say displacement, it will be on displacement. So, and if it is depending upon the derivatives of displacement, which is called the natural boundary condition or the Neumann boundary conditions. So, if you have any structure, you may have a boundary which I call S1, where you have u equal to u naught, that is the primary dependent variable is specified, or you may have some tractions where we call the T equal to Ti. So, this will be on different surface S2. So, this traction Ti will be related to the stress sigma ij into Nj, where Nj is the outward normal, that is a n vector, which is an outward normal to the surface. So, in summary, we have 15 equations, and for the 15 unknowns coming from the equilibrium equations, strain displacement relation, stress strain relation, and in addition it has to satisfy the boundary condition on surface S1, which is the Dirichlet boundary condition, and on the traction boundary condition it has to satisfy the Neumann boundary condition. Let us come into the next level. Let us understand, because the fundamental objective of this lecture is to bring in the energy theorem. So, let us actually explain what does energy and work mean. Suppose you consider a body under action of some forces, and the force vector will have components in both x, y and z direction, which is called fxi, fyj and fzk, where I, j, k are the unit vectors in the 3 coordinate direction. If the body undergoes small deformation, which I call du, which has 3 components again, du in x direction, v in y direction and w in z direction, and the work done is nothing but force into displacement. So, in terms of vector, it is a dot product of f into du, which is given by this. So, the total work done, this is the infinitesimal work done, what we have defined. Total work done is integral between the displacement u1 to u2, the dot product of that. So, if we plot this in a pictorial view, if we have the force displacement relation given by OB here, the area under OB is what the work done. So, we can actually fit in the curve as force is related to displacement by this relation F equal to k into u, where k is some proportionality constant. So, basically it is amounts to taking a small strip within this region and integrating this. So, this basic expression is basically says the area under OAB. So, let us take a system. Suppose you have only a 1D state of system where the force Fx is related to k into u to the power of n, and now we write this equation by using this definition and substitute for Fx k into un and integrate it, we get this. So, the total work done depends upon the exponent n. If n is equal to 1, that is if you have a linear variation, then the area under this curve is just a triangle. But if n is other than 1, it has a complex variation and it depends upon the value of n, the total work done. On the other hand, what we have done right now is we have taken only the area under this. Suppose we take the area over this, we can again write the work in a totally different notation, not in terms of the variation in terms of displacement, but the variation in terms of forces. So, we can have u into df. So, we take a small strip here, that is of df force, and integrate between the two force level F1 and F2. So, what do we get here? So, we will consider the same system Fx to k into un. Since we are varying f, so we have to express u in terms of f. So, we will rewrite this equation in this form. When we do that and we plug in this equation into this equation and integrate between starting 0 to f, we will get a new equation which can be written in this form. Note that when n equal to 1, the W star based on force is equal to the W which is based on displacement, whenever the force relation is linear. When the force relation is non-linear, these two values W and W star are totally different. So, what do we conclude from here? So, equation 1 and 2, although are the definition of work, their values are different. Equation 1 is called work, whereas the equation 2, that is this, is called complementary work. So, we use W for the displacement based analysis and we use W star for the force based analysis. So, let us come to the second important aspect of the energy theorems, that is the strain energy. So, we all know the second law of thermodynamics, which says that the total energy E is equal to the energy due to the mechanical work, that is WE, and the heat dissipated due to the performance of work, that is WH. In most of our analysis, we consider that our thermal process is essentially adiabatic. That means we assume that WH is 0, and in addition we also assume that the mechanical work is done by forces which are gradually applied, not suddenly applied. So, those forces contributed due to inertia, that is the kinetic energy, is 0. So, the total energy E is equal to the energy done by the mechanical work. So, we start with this premise and we continue our analysis. Now, let us consider a 1D state of stress and try to relate this energy in terms of the stresses and the strains. So, here we take a body, a small representative volume of the body of length dx, dy and dz, and write the free body of the stresses. So, we have the stress on the right face sigma x, and the displacement is u, whereas on the left face we have an incremental. So, this is not same, it is changing, and it is changing by a small factor here. So, that is d sigma x by dx into dx, and similarly the displacement is also changing from u plus du by dx into dx. So, this is the incremental change between the right face and the left face. Now, let us sum the forces on the let us find the total work done by these stresses on both the left sides and show what is the difference. And this difference is what we call is the change in strain energy du. So, on the right face we have stress multiply the area of the cross section, which is dz into dy, which is here, multiply by du. On the right side we have sigma xx, this component of stress, multiplied by dy and dz again, and multiplied by the change in the displacement, which is given by this. We also assume there is a body force B, and this body force has the unit of force per unit volume. So, we take this body force multiplied by the volume of the element, which is dx, dy and dz, and we simplify this, we throw out all the higher order terms, and when we do that we get this quantity. Okay. We group this. So, this is got by simplifying this expression, and if you look at this, if the body is in the 1D state of stress, this is nothing but the equilibrium equation. So, this goes to 0, this is not present. So, only body within the expression this exists, and if you look at it, du by dx from our strain displacement relationship is nothing but epsilon x. So, which can be written as du will be equal to sigma x into d epsilon xx. Now, we introduce the concept of what is called strain energy density, which is nothing but strain energy per unit volume. Hence, from the above expression du, we can say which is equal to the change in the strain energy density is equal to sigma xx into d into epsilon xx. So, the total strain energy density is nothing but integral 0 to epsilon xx sigma xx into d epsilon xx. And once we determine the strain energy density, we can write the total strain energy is equal to Sd into dV. So, this is the definition of the strain energy. So, one for which we have to integrate the strain energy density over the volume, and strain energy density is a function of the stresses and the differential strains, and so we need to integrate this with for two strain levels. So, the total strain energy is defined by this equation. So, drawing the analogy between the force and the work, we can again draw the analogy between stress and the strain. If the stress and strain is related by this, and this is the relation that it holds good, obviously there may be, if epsilon equal to 1, we have a linear relationship, which is the constitutive model which we talked just a few minutes before. And now, if you take this and plot it, and the area under this curve is basically the strain energy, and the area under the curve above this is called the complementary strain energy, and one is used for displacement based analysis and other is used for force based analysis. So, what we have derived is only for the 2D state 1D state of stress. So, we can also extend this by using the constitutive model, and I will just write one expression for the strain energy density for a 3D state of stress would be equal to 1 by 2 E into, we have sigma xx square plus sigma yy square plus sigma z square minus nu by E, where nu is nothing but the Poisson's ratio, into sigma xx sigma yy plus sigma yy sigma z plus sigma z sigma xx multiplied by 1 by 2 g into tau xy square plus tau yz square plus tau zx square. You can also express this in terms of strains by using the constitutive model. We can say Sd is equal to E times nu divided by 1 plus nu into 1 minus 2 nu divided by half. Here you will have epsilon xx plus epsilon yy plus epsilon z whole square plus g into epsilon xx square plus epsilon yy square plus epsilon z square plus g by 2 into gamma xy square plus gamma yz square plus gamma zx square. So, this if you put the expression of the constitutive relation in the strain energy density equation, you can get this. So, you can extend it for that. We, for the sake of simplicity and understanding, we derived for 1D state of stress and it can be extended. Now, we will come to some of the energy functional the definition of it. We talked about it little bit in the last lecture. We will go a little more detail in this lecture and see what it means. So, what is an energy functional? Energy, the formulation of finite elements requires energy functional. So, the energy functional is basically has a broad definition. If you take a calculus of variation, this is a broad definition and it depends upon the spatial variable or the independent variable, the dependent variable w, its gradient with respect to x, the second order gradient and so on, and where the domain A and B are the 2 points on the domain. So, let us see that how does it translates to some of our conventional structures like beam. So, before going into it, let us talk about some of the properties of this functional. A functional is said to be linear if it satisfies the condition, that is, if you have a functional alpha w plus beta v, where w and v are some two functions or the dependent variables, then if we can write this as alpha into f of w plus beta into f of v, then we call that such a functional is linear. A functional is called a quadratic functional when this functional alpha into w, where w is the dependent variable and alpha is some constant, can be written as alpha square into I of w. One of the key things what we need is in the functional analysis is how do we define a inner product of two functions p and q over the domain V. So, the inner product is nothing but the integral of p times q into dv integrated over the domain. So, in fact, the inner product itself can be thought of as a functional. So, now having defined this functional, when do we say that the differential equation is a completely well posed problem once we have this following equations to satisfy. That is, if LU equal to F, where L is a differential operator defined over a domain V and it has two surfaces tau, where in one surface the Dirichlet boundary condition is specified and in other surface where the traction boundary conditions, that is the Neumann boundary condition is specified, and L is a differential operator. For a beam it is d4w d4 by dx to the power of 4, for a rod it is d square by dx square, and for many other things it could be many things different. And u naught is the specified value over a domain tau. If u naught is 0, we call it as a homogeneous boundary condition. If u naught is non-zero, it is called non-homogeneous conditions. So, that is basically the way you solve is totally different. So, what are the properties of the differential operator? There is always a functional for a given differential equation provided the differential operator L satisfies the following condition. That is, the differential operator L requires to be self-adjoint for you to have a functional. What do you mean by self-adjoint? If you take an inner product of two functions u and v, where u and v satisfy the same boundary condition, then LUV must be equal to u into LV. So, if this the condition satisfied, then the functional will exist, and such a condition is called self-adjoint or symmetric property. Other thing is the inner product of the function with itself should be positive definite, that is the LU times u should be greater than 0. This is another condition for the existence of the functional for a given differential equation. If these two conditions are satisfied, then we can use this expression in order to get the functional. That is, if LU equal to F, where F is the forcing function, then the functional, the energy functional what we call is LW times W minus 2 W into F, if this is the total expression that gives you the functional. We will actually see this for a beam as we go along. So, now let us derive the governing equation for a beam. So, what we use is the governing equation for, we will do things. First we will say we know the governing equation. If we know the governing equation, we will see how we can derive the energy functional. And the second part we will say, if we know the energy functional, how will we come back to the governing equation. Both we will do, taking beam as an example. So, here this is the governing equation and the differential operator is given by this, that is the fourth order operator here. So, now we will take a inner product, that is LW times W, which is nothing but EI d4W by d into W, and we will integrate by parts. We have done this in the last class, we will do again here. So, when we do this, so this is my first function and this is my second function. So, the integral is integral of first function into, I mean the first function into the integral of second function is EI d cube W by dx cube, evaluated at x equal to 0 and L, which is our domain length, minus the integral of second function, that is EI d cube W by dx cube, into differential of the first function. If you look at these boundary terms, the first is basically the deformation, W, transverse deformation, and second is the force. As I said, it always comes in pairs, the essential and the Neumann boundary conditions. So, W causes the shear force and shear force causes W. So, it is like cause and effect. We talked about it in the last lecture. So, similarly, this is basically evaluated W of 0, shear force of 0, and W of L and shear force of L. So, we can write this expression, and again we have this. We again use integration by parts for this portion. When we do that, we take this as a first function and this is second function. So, we say first function into integral of second function is EI d square W by dx square, evaluated at x equal to 0 and L, plus we have this term. So, if you look at this term is the slope, that is the rotation of the cross section for a beam, and which is caused by the moment EI d square W by dx square. So, the slope causes moment, moment causes slope. So, they are cause and effect, as we talked about in the last class. So, if we expand this, this is the moment at L, moment and slope at L, slope at 0 and moment at 0. So, when we put these things together, we have this, and this is nothing but d square W by dx square whole square. Okay. And if you look at this, for any beam, either this is 0 or this is 0. So, this does not exist. So, but this process will throw us up what form the natural boundary condition takes, which would otherwise would not have been possible. So, for all these are the probable condition. If the beam is fixed, we have slope is 0, displacement is 0, and if it is a free boundary, we have either the shear force 0 and the moment 0. If it is a hinge boundary condition, we have the displacement and moment is 0. So, either case, either one of them goes to 0, so that the boundary conditions are exactly satisfied, and this terms become the energy functional. And we have derived the expression that the other way is to get from the calculus of variation. We have shown that LW is nothing but 2 into this one, and the total functional can become this, which is exactly what we specified before in the a few sections back. So, basically what we are saying is, if there is a differential equation which is self adjoint and positive definite, there is a functional which we can use for formulating our energy theorems and also the finite element methods. Now, let us go to the important symbol, the variational symbol delta, and the delta is basically saying how the particular variable varies over the domain, and it acts like more like a differential operator in calculus. We will be using this operator more and more as we go along. So, now come back to energy theorems. So, one of the things principal things that we are talking about in the energy theorem is the principle of virtual work, which is the heart of the FEM. We talked about the principle of the total potential energy in the last class, and that is derived basically from this equation. So, what does it say? If you have a body having certain constraints, and if you give a virtual infinitesimal displacement to certain parts of the body, and the body deforms in a manner where the boundary conditions are satisfied, then if that is the case, the total virtual energy due to external force is equal to the virtual strain energy. This is the heart of my FEM principle. So, let us actually derive this. So, if you again I will take a body here, and if you have this boundary constraints and you give a virtual displacement some delta u to some position here, and you have this body tractions all over acting, and this deforms in a manner so that the kinematic constraints are not violated, okay, then we have that the total energy W e will be equal to integral over the surface. I call this is the surface where the traction is acting, T I into U I. It has 3 components into ds over the surface, and if Bi is the body force per unit volume, this is over the volume Bi into Ui dV. Okay. So, essentially what we are saying is this is the work done by body force. So, here I equal to 1, 2 and 3, okay, corresponding to 3 coordinate directions. So, we said that my Ti is related to stress sigma ij into Nj initially. We substitute this here and we get this is equal to sigma ij Nj into Ui into ds plus integral Bi into Ui dV. Now, this is We. We take a variation of this, as I said, which is equal to, this is over the surface. We have over the surface, we have sigma ij Nj delta Ui, because we are varying only the displacement, not the stresses, into ds plus integral over the volume, which is Bi into delta Ui into dV. Now, if you want to proceed further, this is a surface integral that needs to be transferred either into a volume integral, or this volume integral has to be transferred into surface integral, where now we use the divergence theorem, which is most theorem in vector calculus, which says that integral over the volume del dot u is equal to u dot n of the surface, where your del is nothing but is a gradient vector d by dx of I plus d by dy of j plus d by dz of k, where ijk is the unit vector. Now, we use this theorem. When we use this, so we can write delta We will be equal to, we can say that sigma ij into delta Ui into Nj ds plus integral Bi into delta Ui into dV. So, this is in this form. So, this I can write it as essentially d by dxj, this is over the surface, this can be written over the volume d by dxj into sigma ij into delta Ui dV. So, this is converted into a volume integral and into V into Bi into delta Ui dV. Now, I can differentiate this with respect to space and group it together. So, when I do that, I can write it as integral over the volume. I will have sigma ij into d by dxj into delta Ui into dV plus integral of volume into delta Ui into d by dxj of sigma ij into dV plus integral of Bi into delta Ui. I am sorry, this is over the volume Bi into delta Ui. So, now what we do here is we club these things together. So, this is delta WE. So, we club these things together and we say sigma ij into d by dxj into of delta ui dv plus integral over the volume delta ui into we have d by dxj of sigma ij plus bi into dv. So, essentially what happens is this is the equilibrium equation, which is equal to 0. So, we scratch this out to 0, we are left only with this. So, delta WE will be equal to integral over the volume, which is sigma ij into, I can take modify a little bit, I can take delta outside and I can say this is dui by dxj. And we know that this is the definition, dui by dxj is nothing but my epsilon ij, that is the strain displacement relationship. So, we can write delta WE is equal to integral over the volume sigma ij into delta of epsilon ij, which is nothing but delta u. So, we have proved that delta WE is equal to delta u. So, this is a fundamental principle by which we need to do this. So, now we talked about the total potential energy in the last time and we said that finite elements will be basically derived from this equation. So, we know that delta u is equal to delta W, and if we designate delta W as V, negative of the V is equal to negative of the total work done by the external forces. We call it as potential of forces, then delta of u plus V equal to 0, which is the u plus V is the total energy pi we talked about, and that is how we get the theorem of minimum potential energy, which we used to develop the theoretical basis in the last lecture. So, now we see that where this theorem is coming from, it is coming from principle of virtual work. So, basically this principle says that this is we cannot solve the governing equilibrium equations exactly. We are trying to find an approximate solution, and an alternate statement of equilibrium is the total minimum potential energy. If this condition, if the total variation of the energy is equal to 0, we say that the body is in equilibrium. So, it is an alternate statement of equilibrium that we will use for this condition. So, that is why this is the backbone of the finite element method that we will be talking about, or we talked about little before. So, let us use now the inverse way. Suppose we know the energy functional, can we construct the differential equation, and that is where we use the principle of minimum potential energy. So, we take the same beam, we know this is the energy function, we derived it, and this is the potential of external forces because of the uniformly distributed load, and the total work done is the negative of the work done by these forces. So, we take the total energy is the energy due to the internal forces and the energy due to the tractions, that is the distributed force. We take a variation of this. When we take a variation of this, we have EI into this 2 gets cancelled because of differentiation. We have d square W by dx square into variation of this portion minus into variation of delta W, because we are only varying the displacements in the finite element methods. In the force based method we will vary forces. Invoking the variational operation, we say we have this. So, I can tune it, I can take this differential out and put the variational operator here by this way. Then we again integrate part by part. We do not want to do that, we have done this. So, we have got this equation which will be writing in terms of the moment and the shear force, slope and the transverse displacement, we get this. And we said that for any beam cross section these terms will be 0. So, what is left is only here, and since delta W is arbitrary, it cannot go to 0, the term inside the bracket should go to 0, and that becomes your equilibrium equations. So, you can derive the energy functional from the governing equation, and you can derive the governing equation from the energy function. We have shown both. We can use these variational principles to do that. We can also do much more. In many structural mechanics problems, we have used what is called Cauchy-Glenow's theorem. So, Cauchy-Glenow's theorem is a very famous equations for many civil engineers to solve many of their problems. We can derive this from the principle of minimum potential energy. So, what we will do? So, basically if there are a body subjected to n concentrated loads, which we call P1, P2, P3 and Pn, okay, and each of these is dependent upon the displacement Qn, then we say that strain energy is a function of Qn, which, and according to the theorem of minimum potential energy, the total work done by the external forces is minus V. So, we have put this in this form here, and since this is a strain energy is a function of this Qn, we write this, we expand this Qn by using a chain rule, which is du by dq1 into delta q1, du by dq2 into delta q2, etc. And we expand this in this form. So, now we group all q1s, q2s, q3s. When we do that, we get this, and in the tensorial form we can say du by dqn minus pn is equal to 0, or du by dqn is pn. This is the famous Cauchy-Glenow's theorem. So, which says that if I want to find out a load at a particular point, you take the total strain energy and differentiate with respect to the displacement at that point. The next important principle what we want to discuss here is the Hamilton's principle. What is this Hamilton's principle? It is nothing but it is the principle of minimum potential energy under dynamic systems. So, in the principal potential energy we derived based on the assumptions that the loads are gradually applied. When the loads are suddenly applied and over a short duration, the dynamic effects will come into picture. So, to handle this, it was way back in 1800 Sir William Hamilton propounded this theorem, and which has a very fine theoretical basis. We would try to derive this equation by using principle of minimum potential energy and see how we can do this. So, consider a mass here which is acted upon by a force F, which has three components Fx I, y, Fyj and Fzt, all are time dependent, and let this mass be located at a position vector r, which has a coordinate xi, yj and zk, and these forces can be further divided into the conservative force and the non-conservative force. The non-conservative force are because of damping or any other force that is not generated due to the loading, because of the phenomenon of the material per se, and the conservative forces are those that are caused by the generation of the internal forces because of the external loading. Now, if this mass is given a small virtual displacement, then the position vectors become delta ui, vj and wk. Okay. So, when doing so, the mass moves from position 1 at time t1 to position 2 at time t2 according to the Newton's second law. So, if we do that, and such a path is called the Newtonian path. If you write the equilibrium of mass in these three directions, we have Fx is equal to, by Newton's second law, F is equal to mass times acceleration, u is the acceleration in x, displacement in x, so u double dot is the acceleration in x direction, v double dot in y direction and w double dot in the z direction. So, the Fx has to balance each of these. Now, we invoke the principle of virtual work. So, we multiply this with the virtual displacement delta u for the x component, delta v for y component and delta w for z component, and we rearrange the term by this form, all the inertial components in one region and the force component in another, and we integrate between time and t1 and t2. So, here u double dot we use integration by parts, we call this integral I1, this is I1, and this is I2. So, when we do that, when we the I1 will basically become first function into integral of the second function, which is u dot, like that for 3, and you have u dot and u double dot, that is there by integrating by parts. And if you look at it, delta W at each of these points T1 and T2 should go to 0, otherwise the existence of the conservation loss is not valid. So, this goes to 0 here. So, this is left by this. So, only this portion is left. When we actually do that, we get this one. So, this is the basically the m by 2 into delta of u dot square, v dot square and w dot square. So, mass into velocity is basically the kinetic energy. So, we get delta of t into w dot. So, we take the next portion of it I2, which is the can be split up into both conservative and non-conservative, and each has x, y and z component, and we can write it in this form. Okay. So, the second integral here is a non-conservative, that is basically delta of non-conservative, that is the work done by the non-conservative forces, which we can write it as WNC. But we invoke now the Castigliano's theorem. The conservative forces are related to du by delta u by small u in the x direction, y direction and z direction. So, when we plug this portion is nothing but delta u. So, if we do this, so we get the second integral becomes this, and the overall Hamilton's principle is given by this. So, this is the principle which we need to use for the cases where we are using the dynamic equilibrium. So, it is essentially a principle of minimum potential energy type principle under the dynamic conditions. So, when the T is 0 and W is 0, this basically becomes the theorem of minimum potential energy. So, now let us see how we can derive the weak form of the governing equation. We just dealt with the weak form of the governing equation for a general system in the previous classes, for a general differential equation. Here we will again take this particular example of a beam, which is a fourth order system, and generate the weak form of the equations. So, we said that we take the governing equation and weight it with a function, and that function and integrate it. And when using, we have to use integration by parts. In doing so, we will be getting a set of equation which is called a weak form, and which is the starting point for our FEM formulation. So, a set of a strong form of the, before going to weak form, what is a strong form? A strong form of a governing PDE is the one which is shown here, and this form, this governing equation is subjected to a set of the Dirichlet boundary condition, and in this case for a beam it is on slopes as well as displacements, that is W and dW by dx, and the Neumann boundary condition, that is on moment and the shear force. So, this is the strong form, and you see that strong form is always order higher. We are having a fourth order system here. So, we can solve it exactly, we get 4 constants, and the 4 constants corresponds to the 4 boundary conditions, possible boundary conditions, that is 2 Neumann and 2 Dirichlet boundary conditions. Now, we reformulate the problem into a weak form. A weak form is a variational statement of a problem in which we integrate against a test function or a weight function, and the choice of weight function is up to us. We discussed this in length in the last lecture. In doing so, we are relaxing a problem a little bit. Instead of finding an exact solution, we are trying to find a form of the equations which is the governing equations or the equilibrium equations, which is amenable for numerical solution. So, in short, we can say that a weak form satisfies the strong form in an average sense over the domain. So, now what we are looking is not W, but an approximate solution W bar. So, when we substitute this into the equation, we said that we get an error function, which we discussed in the last time, and this error function needs to be weighted in order to find the weak form of the solution. Now, why is it called weak? Is it a weaker statement of the problem? That we will come a little later once we find out the weak form of the solution. But one thing is very clear, that the solution of the strong form will also satisfy the weak form, but not vice versa. That has to be very clear. So, choosing the test function, we can choose any function v. We have seen, we have for a typical differential equation, we have chosen a whole bunch of functions in the last class and shown that the variation, the approximations or the accuracy of the solution varies with the choice of these weight functions. So, let us choose some v here that also satisfies the homogeneous boundary condition, wherever the actual solution satisfies the Dirichlet boundary condition. Okay. Suppose u equal to u naught equal to 0 at some boundary, the choice of that function when you substitute that coordinate should go to 0 at that function. That is fundamental. So, we will see why this helps us sometime later. So, in our example, we need to have w at x equal to 0 and the v at x equal to 0 and the slope at x equal to 0 and the same slope for the test function v equal to 0. They are exactly matching with each other. So, we plug into the equation, we again integrate by parts. We have done this many times, we will not do this again here. So, we will get a set of function where V bar is the shear force, m bar is the moment at this location, and you have a test function W and V here. So, this is in general is the weak form of the solution, and this is the starting point. Now, to start the FEM, what we should do? We say that W bar is equal to V. When we do that, this becomes an energy functional, which we will use it in the theorem of minimum potential energy and do that. If we do not want to do that, if we want V different from W bar, then it becomes a weighted residual technique. Then we come up with a new integration scheme, and this is where the link between FEM and other methods are there. All for everyone we need a mesh, and how we define the test function defines what kind of method we have. When W bar equal to V bar, which is essentially the Galerkin method. So, when we have such a thing, then we are in a position to say we have either constructing FEM or we are constructing different method depending upon what we choose. So, the above equation is called the weak form of the differential equation, as it requires reduced continuity requirement. Let us say what it is. In the original, so the highest derivative is d square w by dx square here, whereas the strong form had d4 w by dx 4. So, any equations, any assumption we need to have at least the fourth order derivative should exist. We have a stronger continuity requirement for the strong form. Here we do not have it, we have only a reduced order continuity is required, d square w by dx square. So, whenever we choose a test function, d square w by dx square should exist, which is relatively relaxed form of the restrictions on the governing differential is relaxed a bit, and that is the advantage of the weak form over the strong form. And this aspect is fully exploited in the finite element methods. So, in summary, what did we study in this lecture? So, in this lecture we studied, basically we introduced the concept of elasticity. We said that where are the 15 equations coming from. We use this equation of the elasticity to study the concept of work and energy and associated energy theorems required for the finite element formulation. We studied in detail the principle of virtual work, principle of minimum potential energy, Cauchy-Glenow's theorem, Hamilton's principle, and said how they are linked up to FEM. We also studied the method to construct the weak form of the governing equation. and the differential for a given differential equation. We also studied some aspects of the calculus of variations and how we can actually construct the functional, what are the restrictions that the differential operator should have in order to have a functional. So, in the next class we will actually go into details of FEM formulations and how these theorems can be exploited for a variety of structures to formulate various elements. Thank you.